So let's do some more step 2 questions. This is 2010 question 2. This is the first question in the Trig booklet for step 2 that's on the Millennium Maths website. I'll put a link below this video, hopefully, if I don't forget. Anyway, first we're going to do this proof, which is something that they ask you to do a lot. So maybe just have this one basically memorized. It's cos 3x equals cos 2x plus x, of course, which you can break down to be this based on just the double angle formula for cos, or the compound angle formula for cos, I should say, where 2x goes here and x goes there. It's just cos minus sine. Then cos 2x I just know is cos squared minus sine squared, and sine 2x is 2 cos x sine x. This one, they want us to write it all in terms of cos, so let's write this as 1 minus cos squared, which will make this 2 cos squared minus 1, because there's a double minus in there somewhere. Expand all this out, and you end up with the right-hand side. You want you to do the same for sine 3x. So again, left-hand side is sine 3x equals sine 2x plus x. Sine is the one that goes sine cos plus sine cos, just the other two ways around. Of course, do the double angle formulas again. It wants this one in terms of sine, so I'm going to write this cos as 1 minus sine squared, which makes this whole thing 1 minus 2 sine squared. Of course, this cos squared can become a 1 minus sine squared as well. I did that up here as well. Sine squared becomes 1 minus cos squared. Anyway, expand this out and collect it together, and you end up with your thing for sine 3x. Good. Again, that is asked lots at the start of lots of step 2 questions. You should probably just know that. Anyway, let integral of alpha be this, where alpha is just where it's integrating up to. Show that it's this. Okay, well, we just showed that 4 sine cubed, if we do a bit of rearranging, is going to be this. We can double everything as well to just put it straight into here. 7 sine x minus 6 sine x is just sine x, so we're going to do minus 2 sine 3x will be plus 2 sine 3x. Integrate this is super easy. Sine integrates to minus cos, and sine 3x integrates to a third minus cos 3x, which will become a 2/3 because of this 2 here. Put in alpha, put in 0. When you put in 0, you get cos of 0 is 1, so that makes a minus 1, and cos of 3, 0 is still 1, which is minus 2/3. So we get this, which makes the minus or a plus 5/3, which is where that comes from. So that's fantastic. And then they've just said C is cos alpha. You can replace this cos 3 alpha going back into here. You can replace the cos 3 alpha with this. That's 4c cubed minus 3c. And eventually everything ends up being exactly the way that you wanted it, because the 3's cancel here, so you get plus 2 of them, minus 1 of them makes plus 1 of them. And yeah, that's exactly what they want you to go. Write down the value for which C, for which I of alpha is 0. Well, I of alpha is 0. This isn't the easiest thing ever to solve, but you could just look at it and go, well, if C was 1, then minus 8/3 plus 1 is minus 5/3, is it? Plus 5/3 is 0. Amazing. You could also just argue that from the basis that if you want the whole integral to be 0, you could integrate between 0 and 0, thus choosing alpha as 0. Either way, C is 1 or alpha is 0. Alpha is 0 causing C is 1 is really what they want you to say. But yeah, that's all good. That's all done. Eustace is a moron, so he believes this. Okay. Show that Eustace would obtain the correct value for I of beta, where this is. So I of beta, remember, was this integral. They've just replaced beta with alpha for reasons that I don't understand. We already evaluated it to be this, assuming that cos is now, or C is now cos beta. So, okay, well, let's just use Eustace's rule then on this to say that I of beta is apparently 7 sine squared x over 2 minus, raise that to a 4 divided by 4, 2 sine to the 4x. So this is not what this equals, but according to Eustace it is. So, okay, that's fine, that's integrated, nice and easy. Now we're just going to put in beta and put in 0. Of course, when we put in 0, the sine of 0 is a 0, so that just all goes away. And we get this. Now let's write that in terms of C, C being cos beta. A sine squared beta is 1 minus cos squared, so that's 1 minus c squared. Sine to the 4 of beta is 1 minus cos squared all squared, because it's like sine squared squared, sine squared all squared, so it's 1 minus cos squared all squared. So we get this. And now, to find values for which Eustace is correct, we're just going to set the thing that is actually correct equal to the thing that he's got, and we're just going to ask when that's correct. So let's do that. We've got a bit of expanding to do. It's all just basic algebra. Expanding that first, obviously, then timesing by minus 2, we get this. And then I grouped everything together. I was a bit lazy with it. I grouped everything together and I eventually got this. Now, this is a quartic equation. So solving it is hard, but I'm only really supposed to show that he would obtain the correct value if cos beta was minus a sixth. So, well, that's a big hint. I'm just going to pretend I'm doing factor theorem here to try and find solutions. And wouldn't you know, what I'm going to do first is I'm going to try c equals minus a sixth. I just have a feeling that that might work, you know. I just have that, you know, spidey sense that that might be the correct thing to try, just to really, really find a solution to this. So, okay, I'm going to put in minus a sixth in. Now, I'm obviously not going to actually evaluate this because it's a non-calculated exam. Obviously, this end bit cancels, which is super helpful. Now I can divide everything by minus a sixth, because why the hell not? And now I can times everything by 6 cubed, because that just seems like an obvious thing to do. So just times everything by 6 cubes. All of this goes away except for the minus. This goes away, you add another 6 in. This goes away except for the minus, you add 2 6's in. 6 squared is 36, halved is 18. This makes 48 over 3 is 16, and wouldn't you know, it makes 0. Fantastic. So c equals minus a sixth is a solution to this, and so therefore Eustace would obtain the correct answer with his stupid method, if cos beta was minus a sixth. Find all the values, alpha, for which he would obtain the correct value. So, okay, well, we're just, now they've apparently gone back to I of alpha, but that's fine. We're just going to say that c is cos alpha now. We're still solving this equation, right? Because all the maths is exactly the same up to here. We evaluated his way of integrating, we evaluated our way, we set them equal, we got this quartic here. So everything's all the same, except I now know, of course, that cos beta, or cos alpha really, because now we're back in the alpha world for some reason, is equal to minus a sixth. So that means if I maybe times everything by 6 first, I think is what I did, I now know that 6c plus 1 should be a factor of this, or is a factor of this, because c equals minus a sixth is a thing that works. So I could do some polynomial division, but I'm not going to. I'm just going to spot all the coefficients one by one. So obviously this needs to be a 2c cubed, because otherwise I'm not going to get 12c to the 4. At the end we need a 1, because 1 times 1 is 1. And then we just need the middle two terms, which I'll just call a and b for now. Looking at b, I need, if we just look at the c's over here, maybe we've got 6 c's over here. We've got 1b plus 6b, sorry, plus 6 c's over here. So just thinking about how we're getting c's, 1c plus 6c must be 6c. So that means b is 0. So that's good. And now looking at the a's, let's maybe look at the c cubes now. We've got 6ac cubed plus 2c cubed is minus 16. So that's 6a plus 2 is minus 16. Take away 2 divided by 6 and get a is minus 3. So this will be our factorization. It's not too hard to spot at this point that c is 1 is obviously a solution. 2 minus 3 plus 1 is 0. So let's break this down into c is 1. I'm just finding the other solutions now, of course, because I've got down to a cubic. It's slightly easier. So c equals 1, so therefore c minus 1 is a factor. Again, just spot the coefficients. This needs to be a 2c squared. Obviously, this needs to be a minus 1, because minus 1 times minus 1 is plus 1. And in the middle here, let's just spot this. We need no c's. Right now, we've got minus 1 c's. So we need another minus 1 c's to make that all cancel. And if you check the c squareds, this all also works. That's fantastic. C is 1 still solves this. It's 2 minus 1 minus 1. So therefore, we can remove another c as c minus 1. Of course, this is just a quadratic, so you can just factorize it using GCSE maths if you want. But anyway, you get down to this factorization, which is fantastic, because now you have the solutions of c is minus a sixth, c is 1, and c is minus a half. Again, this one is just repeated, so it doesn't matter. Now, this one is fine, right? Because if you go all the way back, by the way, there are no restrictions on alpha at all. If we go all the way back to the previous bit in the question, I didn't have to do this. You could have just trusted me. But if we go all the way back, there are no restrictions on alpha at all. So when we're doing this last bit, we need to firstly state all the solutions, because there's no restrictions at all. So we need to state all the solutions, which are 0, 2 pi, or more generally 2n pi, where n is just any integer number. Then for this one, we're obviously going to have the solutions of, well, minus a half. That's going to be, so you go past pi over 2, you go another pi over 6 along. So that's going to be 2 pi over 3, I think, is where you get to. Plus all the 360s, you can go from there. But also, if you just start at minus 2 pi over 3, you can then add this same 2n pi to get all the other ones. Actually, what I actually did, though, was I went to 5 pi over 3, and then added all the integer ones from there, which is also just as valid. I'm just going pi over 6 back from 2 pi here, which I think is, no, I'm not. Is this even correct? This isn't correct, is it? No, it's not. Amazing. This isn't correct. This should be, what should it be? It should be, well, the easiest way to do it would be to just say it's minus 2 pi over 3, as I was saying before, because you can just, because cos is an even function, right? So you just go with the other ones. And this is actually what I did here, right? Because I actually have to look in the mark scheme here because I wasn't sure what to do with this. Good to know for future step questions. It's expecting your answers to look like this sometimes. This is just what they wrote. Cos inverse of minus a sixth plus 2n pi. Or, of course, because cos is even, you could start at minus cos inverse minus pi over 6. So you could go to the negative of the principal root and then add on your 2 pi's. So interesting that that's the thing that they're expecting you to do. Anyway, I'll move on to this question in just a second when I get some water and get my voice back. Right, so another one here, step 2, question 3 from 2009. Firstly, we're going to start with this little proof, just like the last question started with. Okay, well, we can use this tan formula, which is not in the book, or is it in the book? I can't remember. No, it is in the book, right? This one with a quarter pi and a half x over here. If you put a minus there, that makes that a minus and that a plus. So that just all goes in there. Tan of pi over 4 is 1, so that just becomes this. And yeah, we're trying to get to this thing over here. There's a few things you do here. I firstly just chose to times by 1 minus tan and a half over top and bottom, because that gave me this. And then I decided to be a bit fancy. I think there's much easier ways of doing this, to be honest, than what I've done. I think I made a bit of a mess of it, but I was just trying to be fancy. 1 plus tan squared is sec squared, ignoring this middle term. And like at some point, we're also going to have to turn these x over 2's into x's. So I decided to just look at the tan 2x formula by putting a and b equal to each other in here. And then I didn't rearrange this. What I just noticed was, okay, well, if you just replace the x's with half x's, you end up with this. If you break this fraction into 2 pieces and remove this from the numerator and put it outside on its own like this, then this is just precisely that. So this whole thing is just tan x. So that was quite helpful. And as I've said, 1 plus tan squared is sec squared. So that also works quite well. So now I just need to show that this thing is sec. To do this, I just decided to quickly make these substitutions in my head and just write this down and just pray that that got to 1 over c. In fact, no, that's not what I need to get to because of the x over 2's and the x there. So what I do need to get to, and you'll see, is this becomes c squared over c squared, which can become this. These c squareds cancel, so now we've got this. Now cos squared minus sine squared is cos 2x. But of course, both of these coses and sines have a half x in them. So this thing here is just cos of a single x. 1 over cos of a single x is sec x. And so we end up with, or cos of 2 lots of a half x, I guess I could say, which is just sec of x, I guess. Which is, I think, close enough to say that's just right-hand side. Anyway, probably made a bit of a mess of that. I think there were probably easier ways of doing it. Anyway, use star to find the value of an 1/8 pi. So okay, we just want this thing to be equal to an 1/8 pi, I guess. Solve that for x is quarter pi. And yeah, put a quarter pi in here, and we'll get a thing. Tan over quarter pi is just 1. Sec over quarter pi is 1 over cos over quarter pi, which is root 2 over 2, or 1 over root 2, which just makes this whole thing root 2. So it just becomes root 2 minus 1. And that'll be that. Hence, show this thing here. Now, using hence means I'm going to be using this idea, not necessarily this one. So okay, how do we use this idea here? Well, think about 11 over 24 pi. That looks to me like it's roughly going to be an 1/8 pi plus a 1/3 pi, because if you 3 plus 8 makes 11 times them to make 24. So that seems good. And even better, of course, I know the value of tan of a 1/3 pi, so I can just ignore this for now, and I can just use tan of a plus b ideas. I wrote it on the previous slide, didn't I? Tan a plus tan b over 1 minus tan a tan b. I know all of these things because tan of a 1/3 pi is just root 3. Which is just an exact value you should know. If you're not sure about it, just draw yourself triangles and you'll figure it out. Tan of an 1/8 pi has already been found for me, so we end up with this. I can do some expanding out. I also need to do some rationalizing here, I guess. Oh, no, I don't. Sorry. I don't yet. This is precisely what they've got there, just in different places. So that's all fine. Now it's telling me to try and make this into that. Now, I'll say on the record that there is a much easier way to do this than what I'm about to do. The much easier way to do this is to just claim that if this is true, then it must necessarily be the case that this thing times this thing is equal to that thing. And you can just expand it out and check that it is, and it is. If you don't want to do that, you can start on the left-hand side, group the surds together, and then rationalize like this, or at least attempt to rationalize. If you expand out very carefully, you'll end up with this, which is great. And then you could try simplifying up some terms and you'll get this. This is really boring. I'm not going to go over it in too much detail. But you simplify a bunch of terms together. You lower down some surds to simplify those too. Eventually you end up with this. You can halve every number in here to get to this. And then you can just rationalize again. And if you do that, you'll get this. Everything halves again. And you end up with precisely what they wanted you to get. Yeah, probably not the best way of doing it, but whatever. Use star again. So now we are actually using star again to show this thing here. So okay, using star, I need to get to 1 over 48 pi. So okay, let's just, again, set this equal to 1 over 48 pi and see what kind of x value I would need to do that. And wouldn't you know, That's the x value of 11 over 24 pi, which is fantastic because I already know that. I have it right here. So therefore, tan of 1 over 48 pi is just equal to sec of 1 over 20, oh, sorry, 11 over 24 pi minus tan of 11 over 24 pi. Now, tan of 11 over 24 pi, I know, so that's fantastic. Just shove that in. Now, what about sec of that? Now, sec is 1 over cos. I don't have any way of evaluating cos at that angle unless I want to, maybe do the whole thing again using some identity for cos. But you look in the answer and you think, okay, well, here's a big square root over another thing. So how am I getting an object a bit like that here? Well, and also, how could I not think about sec in terms of cos, but instead just relate sec directly to tan? Is there a way to do that? Because I know the thing about tan here. And there is, right? You can just write sec as 1 plus tan squared square rooted. In other words, you can write sec squared as the square root of sec. Sorry, you can write sec as the square root of sec squared. And then you can just say, well, sec squared is 1 plus tan squared. But you know tan at this value, so therefore you know tan squared at this value. It's just this thing squared. And then you can square the whole thing out, and you can, which I did here, took some effort, but I squared all this out. I times this by itself. It was just, it's just all the things times by themselves. There's 4 of those, and then it's 2 lots of all of the combinations of things, which is all of these. Anyway, then you simplify some surds up and you collect together some terms, and that basically is close enough to the right-hand side that I'm just going to leave it there. And that's that question done. Really fun question. I'll see you next time.